but now I believe it's very important to broaden my horizon. So I come to Purdue to continue my research. Okay, so China University of Petroleum is located in the city of Qingdao. You know, Qingdao was once a listed terrorist of Germany. So at that time, they built many European-style buildings, and this is also my hometown. As you can see, my hometown is very, very similar to the city of Lisbon. Okay. After my Bachelor of Engineering, I went to Chengtian University to pursue my PhD. And at that time, my research field including mass transfer and separation, process system engineering, process dynamic control, and industrial waste heat recovery. And I write a final thesis about process integration and intensification of distillation system considering pressure. Decision value optimization is a combine of process engineering and the mass transfer. And as a system professor at DEQTalk, I normally teach chemical process design. I teach Aspen Plus, Aspen Hysis. Also, I teach a course about the process control. We are using Simulink to design PID controller. Also, my research including process optimization. So I normally use the software GAM to build some missing integral programming problem. And recently, I got involved in the process safety area, and I have a recent paper about using the low-pass strategy, that is the layer of protection analysis, into the process design. Also, because my institute at the Nanjing Tech was co-founded by the university and the company is the Zhejiang Supercom Group. So they always send me to the company to build some software problem. For example, we are building the OPS system, that's called operator training system, to train operator on site. Now my project is about electrification of steam methane reforming. This project is supported by NSF Engineering C-STAR project, and is also supported by the US Department of Energy. Now I work with Professor Cornelia Masuku, Rajesh Younger, and Domarasmi Ramakrishna. So the purpose of this project is to drive innovation in the reduction of carbon intensity of the chemical industry, particularly the process of steam methane reforming, because this process is endothermic chemical process. So it's very important to reduce the energy consumption and reduce the carbon emission. So before I go to the electrification, I will share some background data. For example, here, this is the global greenhouse gas emission. As you can see, nearly 1/3 of the isotropanic GHG greenhouse gas emission will come from the industry sector, and chemicals occupied almost 20. So this means this is equivalent to the 6% of the global GHG emission. And most of the emission from direct emission from the combustion of, for example, natural gas is generate heat and electricity. And this energy is used to produce many raw material and intermediate, for example, methanol, ammonia, olefin, polymer. These are very familiar to chemical engineer. But why electrification? In our opinions, we believe electrification can provide two purposes. The first one is decarbonization. Usually, combustion of fossil fuel can generate a huge amount of CO2. But if we use the renewable electricity, for example, if the electricity can be generated from wind or a solid, so it will dramatically decrease the CO2 emission. So this will help to achieving the ultimate goal of carbon neutrality for the human society. So there is a transition trade that from the fossil fuel to the renewables. And the second purpose is improving the energy efficiency and reducing the energy consumption. For example, if you're using the induction heating, this is my current project. If you use induction heating to directly heat the steam methane reformer catalyst active site, it will increase the energy transform efficiency. Or in a distillation process, if you use a heat pump, particularly when the COP is higher, COP means a coefficient of performance. I will give you example later. So about electrification, there are many electrification technologies. For example, from this perspective paper, they list the 4 types: direct heating, hydrogen, electric chemistry, and proxima. As you may see, the electric chemistry and the proxima technology has not very high technology readiness level. So that means they are in the lab scale. But here, the direct heating and hydrogen has a very high TRL. So these are 2 benefit technologies that we might use in our project. So far, we are interested in using direct heating to electrify industrial endothermic reaction and the distillation process. Why? Because the first reason is that they have a very high TRL, and the second reason is because they are easy to retrofit the existing process. This is another paper lists the electrified heating. This technology are all in this tab. Okay. In this paper, they list the electrified heating as 3 types: direct heating, indirect heating, and steam generation. Particularly, we focus on the inductive heating because it can generate very high working temperature. And the resistant heating is also, this heating is one of my colleagues working on this. And also the burner, the e-burner, this can be used to generate steam. Okay. In addition to this power-to-heat technology, we also consider the heat pump. Heat pump is another measure to generate high-temperature steam that using the electricity-based vapor recompression. Okay, I will give you an example here. Okay, this is a decision-making flowchart. The purpose for us is to decarbonize the chemical industry, so it's necessary to ask a fundamental question: where are the greenhouse gas emissions from? If a process is completely driven by electricity, okay, you can use low carbon electricity generated from wind and solar, and you can achieve decarbonization. But what if a process is driven by heat, or it will directly release some carbon into the atmosphere? So the next question is, can this process be done electrochemically? As I said, the electric chemistry has a relatively low TRL, so there's no many processes that can be electrochemically driving. If yes, then you can design novel process with low capital expenditure. But if not, you may consider to decarbonize heat, or directly using the carbon capture technology to capture the CO2 or the methane. If you use the heat, it depends on the temperature. If the temperature is low, for example, lower than 400 degrees C, you can then use the low carbon electric stream. But if it's high, you may consider some low carbon electrical heating like induction, resistance, something. I will talk about it later. Okay, for chemical process design, the oil model is very useful. This is a very famous model actually. Chemical reaction is in the inner layer. So it's the core of the chemical plant. Particular, we are interested in the endothermic reaction because they need energy. And in the next layer about separation and the recycle system, we are interested in distillation. Of course, there has a lot of separation measure, distillation, absorption, pressure swing, absorption, extraction, many. But distillation consumes a lot of energy. and it is used for more than 95% of liquid separation, and the energy used from this process is an estimated 3% of the world energy consumption. In another data, it accounts almost 50% of the whole chemical plants. Okay, so this distillation is very energy intensive. And the next layer is about heat recovery system. In designing a heat exchanger network, we may consider using the pinch analysis. For example, here, you can use this method to determine the minima heat input and the minima heat output. Then, in the next layer of designing energy system, utility system, you may use this to calculate how much energy is needed for the process. Okay, and the water treatment is another problem. It's not in the field of decarbonization. For the reaction, for the electrification of reaction, normally now, the US has a very large amount of shale gas. Shale gas is also a type of fossil fuel, but we believe that so far, completely transit from fossil fuel to renewable is not possible. So there has an intermediate solution. Here is the intermediate solution. We use the fossil result as a carbon source. For example, we use the shale gas as a carbon source, but we use the renewable electricity and as the energy source. For example, this reactor, we use shale gas as a carbon source to produce liquid fuel, but to drive the reactor, we used solid energy, wind energy, and because this process also produces hydrogen, so the hydrogen can be self-used to produce electricity for the process. And another question is that the solid and the wind are intermittency. It changes with time and the weather, climate, something. So it is difficult to build a model for this whole process. One of my colleagues studies resistant heating, but my research is focused on the induction heating. For example, this is the ethane cracking to produce the ethylene and the hydrogen. He studied two types of heating. One is external heating. You can put the coil outside the reactor, or inside resistant heating, you can put the coil inside the reactor. We have done some simulation, and we found internal resistant heat is better. We are still co-author this paper now. But for the electrification of distillation, one of the most widely used electrification measure is heat pump. For the conventional distillation, as you can see, the heat supply in the reburner is wasted in the condenser. So as you can see, the temperature catalyst, this is a condenser, this is a reburner. So it cannot reuse this type of energy to heat the reburner. But what if you added a heat pump here? You compress the overhead vapor, and the overhead vapor will get a high temperature, and then you can use it to heat the reburner. So in this process, the self-heat inside the process is completely recycled by adding the electricity, by adding the work. So there's no more heat in addition. So because the work is normally it's electricity, so the electricity can be coming from wind and solid, so it comes from renewable. It can achieve decarbonization. And the next layer is about electrified heat exchanger network. This is a relatively young research field. But this is the old paper because it only considers the organic Rankine cycle. Organic Rankine cycle is a way to transform waste heat to power. But what if we added heat pump somewhere in the heat exchanger network superstructure? We might get new mathematical formulation and maybe get some new ideal. Finally, layers about the energy system or a utility system. In the conventional utility system, the furnace, the boiler, and the steam turbines, they all relying on the combustion of fossil fuel. And for example, if this temperature is high, you can use this process stream to generate low pressure steam. But the waste heat must be cooled by the cooling water. This is called the ground composite coal. Using this, you can determine which energy is needed. But for the electrified system, we might totally consider the process the process heat generated from electricity. For example, this EE funnel can generate relatively high temperature for the process, and the E-heater can provide intermediate temperature. What if a process needs steam? You can use E-burner to generate steam for the process. Also, for the low temperature process stream, you can use ORC to generate power for the heat pump, or you can upgrade the energy to heat the process. Okay, this is the electrification measure that can be used in the process level energy system. About my current postdoc project, I'm focused on the electrification of steam methane reforming. Steam methane reforming is a way to produce hydrogen. Hydrogen is very important. Normally, you can use water electrolysis to produce green hydrogen, but this technology so far is very high cost. So normally, we are still focused on using the natural gas or a shale gas as a carbon source for generate the hydrogen, although it's a green hydrogen. Okay, this is a conventional top-fire SMR reactor. It's relying on combustion of fossil fuel to generate radiation heat, and the radiation heat will go into the reactor wall, and through the heat conduction, through the wall to gas heat transform, and through the heat convection between the solid and the gas, and finally gets into the catalyst active side. So this process, this heat transform process, is not very energy efficiency. So our work is on using the induction heating to improve the heat transform efficiency and reduce the carbon emission. Okay, for the conventional top-fired SMR reactor, we may use this is the material balance for the Baku gas, and this is the energy balance for the Baku gas. We might consider the material dispersion. We may consider the heat conduction, heat convection, heat dispersion, and solid to gas heat transform. And for the catalyst domain, we might consider the diffusion, and we might consider the reaction heat, and this is the conduction. You see in the conventional process, the heat need to get into the catalyst active side, and the material get out from the catalyst. This is a way of the modeling the process. But now our project is working like this. This is the entire flow sheet for generate from natural gas to the hydrogen. So far we focused on the steam reformer using the induction heater, and the induction heater and the heat from the induction heater is from the renewable energy. Okay, and after this reactor, we may consider electrification of the water gas ship unit, and finally we aim to simulate the whole process. Actually, this is the new electrification of shale gas basis hydrogen production process, and the carbon source is shale gas, and the energy source is the renewables. Okay, when we talk about induction heating, it can generate it. The induction heating is normally generated by the alternating magnetic field. Alternating magnetic field, it can generate a mechanism called hysteresis. This is the main focus in our study. And also, you may consider the eddy coring and mechanism resonance, but these two mechanism is relatively low in our study. Here is a reactor. Here is the reactor. So this is the conventional top-fired steam method reformer. It's generated by thermal. But here, this is the induction heater, induction-heated steam reformer. We use the coil, that wood is the reactor, and this is the alternating coral. As you know, alternating coral can generate alternating magnetic fields. And you can put one of the elements called cobalt. Cobalt. Why we use cobalt? Because we will use a catalyst to produce the hysteresis heating inside the catalyst particle. So if you want to use this induction heating, the catalyst must be used to as a susceptor to be ferromagnetic. So if ferromagnetic elements, including the nickel, iron, and the cobalt, there has a concept called Curie temperature. So if the temperature is over this Curie temperature, for example here, the element will become from ferromagnetic to paramagnetic. That means there's no hysteresis heating. So because the SMR reactor is operating over 800 degrees C, so from this temperature, we may only consider a cobalt element. We should put the cobalt element into the catalyst, and it will generate on-site insomate heat inside the catalyst heat. And as you can see, this is a concept temperature profile. In the normal conventional process, the temperature is at its lower temperature in the center. But here, in the center, the temperature is quite high. So this means the reaction can be working very well under this temperature. So also, because as I said, the heat must be transformed from outside to the inside. But here, the heat can be generated in the catalyst active side, so it will improve the energy efficiency. I will completely I'm still collecting data in this paper, so I will present the whole paper in the coming ASHE meeting. As far as the electrification of distillation, we have done a lot of work. In the conventional process, in the conventional distillation process, the distillation column is completely driven by the combustion of fossil fuel. But in our new design, we wish to use power grid or renewable power combined with the energy storage system to drive a redesigned electrically driving distillation process. This is what we have done. Okay, normally heat pump, for example, the mechanical vapor recompression can be used to compress the overhead vapor to drive the reburner. But here, we need to know that because when you compress a vapor, it might generate some liquid drop that will damage your compressor blend. So it is necessary to superheat the steam before it goes into the reactor, before it goes into the compressor. So you might need to preheat the overhead stream before. Okay, if the process does not need so much energy to drive, you might spread some vapor here to save the power in the compressor, or you might use the compressed stream first heat the reburner and then preheat the stream before the compressor and then go into the condenser. Or another way is to use the this one. You might use to drive the reburner first and then use to do the feed preheating. This is the four method. We are combining this four method as a superstructure. And as you can see, this is a pre-compressor spring. This is the compressor inlet preheating, and this is the feed preheating. We designed this process superstructure, and we use Aspen Plus to design this process. And because Aspen Plus does not very good in the process optimization, so we connect Aspen Plus with MATLAB, and we design optimization algorithm, and we have achieved the communication of data, and to optimize the whole process. Here is an important example. We use this process superstructure in a pressure swing distillation for separating minima boiling azeotropic. So this is a conventional PS pressure swing distillation. It is completely driven by heat. But here we are using the compressor to drive the process. This is also a process superstructure. Okay, this is the result in the conventional process. As you can see, the grand composite curve. This energy must be driven by the medium pressure steam. This process is quite has a very low temperature requirement, so it can be driven by the low pressure steam. Also, some of the waste heat must be taken away by the cooling water. However, in the electrical driving distillation process, as you can see, most this pocket, that means there's no cooling water needed for the process. Also, this is not closed, so it still needs some heat, but this heat can be generated from e-burner, for example, and the complete process is driven by electricity. So this way, it can be used to drive the whole process by electricity. Here is a steady state comparison. For example, here the conventional. This is the result of the conventional PSK, and this is a result of a conventional SHRK. This is it can achieve electrical process can achieve more than 20% of TEC reduction and more than 80% of CO2 emission reduction. Okay. Also, we designed the control structure to see if this electrical process can have the better dynamic performance. Here, this is the control structure for the conventional one. It's very easy. For example, the pressure is controlled by the cooling water, and we use a single end temperature control. The temperature is controlled. The column temperature is controlled by the reburner duty. This is also the single end temperature control. As we added some disturbance, for example, we added some feed throughput disturbance, and all the parameter can return back to the nominal value very quickly. Also, we designed the control structure for the electrical process. As you can see, we also use the single end temperature control loop, but here the temperature must be controlled by the compressor power also. An additional reflux over feed forward controller is added in order to stabilize the whole process. We also do the dynamic performance comparison. As we can see, the control performance is also very good. So we can see if a process has better steady state performance and dynamic performance, we can recommend this process to the industry. Also, we introduce the electrification measure to the extractive distillation process. This is a design framework from the conventional extractive distillation to the final electrified extractive dividing work column. This is the design framework. We also do some steady state optimization project, and we see the electrical process can save approximately 20% total annualized cost compared to the conventional process. We also do some dynamic process design, and we found that new electrical process can be completely under control. So we guess it can be recommended to the industry. This is my future project. Now I'm very, very interested in the electrification. So there is a research field called Power to X. Power to X. Power can be generated from renewable. X maybe means methane, ammonia, methanol, but it needs some additional process. For example, if you want to produce methanol, you might need to integrate with the green hydrogen production. There is a water electrolysis. I am very interested in how to design and modeling the water electrolysis now. Also, you might need the carbon source, but the carbon source can be from the atmosphere. For example, it's called direct air capture, or this carbon source can be come from the, for example, power plant, something. And also, we might need air separation unit to build the whole process. We are going to maybe design some process for production methanol, ammonia, something. Also, because if you wanna drive a process, you must still considering the energy sources. As I said, the wind and the power is intermittent, so it is difficult to modeling the process. So, in our opinion, it is needed to design a simultaneous optimization method that considering the process design and scheduling. Recently, the US NSF has launched a new project that is exploring the space at the times interdependency between electrochemical, chemical industry and the power sector. So in my future work, I might combine these two disciplines to design the whole process that can be used to completely achieve decarbonization of the power system and the chemical sector. So that's all my seminar today, and thank you for your attention.